Hi, good morning, everyone. This is Vishal Ramras, your Slack mentor, and today we have met for the webinar on camera calibration and color spaces. This is the second webinar for our first term of self-driving car nano-degree program. I welcome you all, and we'll proceed with the slides. We'll go through the slides and we'll discuss various concepts on camera calibration and color spaces. In the meantime, if you have any questions, feel free to drop them in the chat message over here and I'll try to answer them. At the end of the webinar as well, we will have some slot reserved for the question and answer section. So starting now, the very first thing about self-driving cars is they are kind of an autonomous system, or you would say an artificial intelligent agent, and it would consist of three parts. The very first step, or the very first part for the autonomous vehicle would be to perceive the environment and try to understand what's surrounding them. Second step, or the second part of their functionality, is to make decisions based on the data which they perceive from their environment. So, for example, if they see some vehicle very close to them, they need to apply the brake, or if they see that the road is very empty, they can maybe speed up, they can maybe accelerate their car. So, such kind of decision making happens in step two, or the part two of their functionality. And the third, or the final part, is the actuation, which is basically whatever decision they have taken in step two, they have to apply that decision in step three by using proper actuators like steering wheel, or the accelerator, or brake paddle, or something like that. So that's the entire life cycle for an autonomous vehicle. It it is broken down into three simple steps, but each step is very complex. It requires a lot of systems working and orchestrating with each other, and communicating with each other and helping each other module, helping all the modules to work in unison towards a common goal, common output. So, talking about perception, 80% of the work in autonomous vehicle or in self-driving car has to be done through its perception systems. Once that's done, the rest of the work is still not that complex, but perception is the eyes and ears for an autonomous vehicle to drive in our world. So now, why camera? So we do have other high quality sensors like radars and lidars, and they provide 3D information of the environment, but they are very costly, and their spatial resolution is very low. Compared to camera, it would provide you a very high spatial resolution, and it's very cost effective. Cameras are being utilized in our day-to-day lives since ages, so it's a very cheap commodity compared to all the other sensors which a self-driving car would incorporate. Now, what does the camera do? It's basically it takes 3D information of the world which it sees, just like our eyes, and it converts it into a 2D representation using some mathematical transformation. The 3D to 2D transformation done by the camera is not so perfect, it's not so accurate. And what happens is, if you would have observed in some of your selfies or other images that the area near the edges of a camera image, it gets stretched, or it gets skewed, or it would have some curvy kind of distortion in it, and it can cause issues in our data representation. So we need to correct for this distortion, this imperfection of the images generated by the camera. And that is exactly what we are going to look in this webinar, about how we can achieve the camera calibration to remove the distortion present in the camera images. So as you can see in this slide, we have an original image which is completely undistorted. It's the real world representation of road having two cars, having lane markers, having trees in it. But now when in the bottom portion of the slide, you will see that the images taken by camera are distorted in some or the other way, due to which the white car is not looking proper, and even you would observe that the lane lines are getting skewed, as you can see in this next slide. So this kind of distortion causes a corrupt data information, which is not good enough for our perception algorithms, for our computer vision algorithms. It can create problems while using this kind of distorted data, this kind of distorted information input in our processing pipeline. So we need to correct that, and um, to get a deeper idea about how this can be achieved, let's look at the camera model. So the very first camera generated by, or I would say invented by human beings, was a pinhole camera. What it has is simply a pinhole, uh, and in that pinhole, the rays of light enters. So on the left side of the slide, the left image, you would see that there is a traffic sign, and the rays from point P to point Q would enter the pinhole camera from a pinhole, and inside the camera, the rays are inverted such that Q is coming on the top and P is coming at the bottom, and the traffic sign is inverted. Such pinhole camera is free from distortion. It does not have any distortion issues in it, because it's simply capturing the rays of light coming from the environment, and those rays are being projected to uh, film, where the exposure of these lights can be stored, or can be captured to permanently retain the memory of the scenery or the image which has been observed by the camera. But on the right hand side, you can see is the model of real world cameras which we are using nowadays. They consist of convex lenses to, you know, concentrate more and more rays of light, so that we get better resolution of the image. But what happens is the convex lens which is used to improve the resolution, it is made up of glass material, and when the rays of light enter from one medium to another, in this case the rays of light enters from air to the glass, or say the convex lens, and then again to the air inside the camera, because of which the rays of light bend to some extent due to different refractive index and according to the Snell's law. This causes the distortion. This kind of distortion is basically radial distortion, which we'll look into detail uh, in the later slides. But this kind of distortion needs a correction, otherwise the edges of the image would look little curvy. It may not look as accurate as it needs to be. So before going in more detail about the distortion, let's look at the camera metrics. So as you know, and in the real world, the image, or whatever we see from our eyes, the real world is a 3D world. It has X, Y, and Z coordinate. Uh, but the image which we see is basically X and Y coordinates. It's a two-dimensional image. So there has to be some mathematics which converts this three-dimensional information into the two-dimensional representation, and there is a conversion constant which is called camera metric C, and that is used to convert the real world object data points into the image data points of the 2D world. So this is just to give you a basic idea about what is camera metrics. We are not going to get in much detail about how internally this conversion happens and what is the formula, what are the equations, or how the camera is implemented. But just to give you an idea that there is something called camera metrics, which can convert a 3D uh, data points into a 2D image. And that 2D image is basically what we are using in our image processing and computer vision. So now let's talk about radial distortion. So it happens due to the lens. If you are using a pinhole camera, you may not, observe this radial distortion. But most of the cameras which we have nowadays consist of lenses. So for better spatial resolution, for better focus. So such lenses are going to introduce the radial distortion, and the image might look like how it is looking in this slide as of now. And this is the most common kind of distortion, and there are three distortion coefficients used to correct this kind of distortion. Another one is the tangential distortion. It happens when the camera lens is not aligned parallel to the imaging plane. So let's talk about not the digital camera, but the camera before that, where we would have a film on which we would the shutter would open and the rays of light would fall on, and due to that exposure of light, an image will be printed on the film, and then we would have to develop those films and get the prints of the images, right? So the let's just assume that the lens is not parallel to that film, but it's at some angle. Due to this, the rays will get tilted to some extent, and because of which the tangential distortion would happen. Similarly, this tangential distortion can happen in digital cameras as well, due to this incorrect alignment of lens, or maybe due to some other reasons. But this is another kind of distortion which happens in the camera images. So to correct this, we have two uh, distortion coefficients, which again we'll look into. Uh, so as you can see, in the bottom we have the real world scene, and then in the middle we have the image which is captured through camera. uh, so they both does not look similar. The one captured by the camera has some radial distortion in it, and our goal is to get an image which is the corrected one, which is identical to the real world scene. And to do that, we need to compute the distortion coefficients, and we need to use those coefficients to undistort our image by calibrating the camera properly. One important point I would like to bring over here is about the coefficient K3. As you can see, coefficient K3 is at last. First we have K1, K2, then we have P1, P2. So K1, K2 represents radial distortion, P1, P2 represents tangential distortion. K3 again represents the radial distortion, but it's placed at last because it basically reflects the major radial distortion, which happens mostly in the wide angle cameras and not in the regular cameras. So sometimes we may not even need to correct distortion caused by, we may not need to correct the major radial distortion, and that's why K3 might not be used. But when you will be working on advanced lane finding project, you will be using K3 as well. You will be correcting that as well while calibrating your images, so that your camera calibration covers whole ranges of camera lenses without any issue. But usually only K1 and K2 will also give you a better correction of the radial distortion. So in order to correct the radial distortion, as you can see in the slide, we have two chessboard images. The left one is captured by the camera, and right one is the real chessboard image. Why we are using chessboard is because it's a high contrast image with a regular geometric pattern, and we have good preliminary data, preliminary information about it, which can be leveraged to do the correction. So on the left image, you see a pink point, which is labeled by the coordinates X and Y. So this data point, if it is to be represented in the real world, then its location would be X corrected and Y corrected in the right image, and the center of the right image, which is the correct image or the real world image, is called center of distortion correction, and it's denoted by the coordinates xc and yc. And what we have to do is we have to find the distance between the corrected coordinates x corrected and y corrected uh, with respect to the center of this corrected image, and that distance becomes r. And we use the formula provided on the right side of the slide in order to correct the radial distortion of the image. So this is about the mathematics, but you are going to use OpenCV function and OpenCV library, and you would use some functions provided by OpenCV to correct the distortion of the camera, to calibrate the camera. So you would not have to do this calculations manually, and we are not going to go in details about this. But at your time, you can of course try to have a graph paper and do some plotting and measure the actual distance and try to see how these equations are working and what kind of results they are generating. In the next slide, we have the steps to calibrate the camera, or I would say the pipeline to calibrate the camera. Uh, the image shows a chessboard in its real world representation. It's not the camera image, but the real world representation. And it shows three coordinates x, y, and z. The z coordinate is going to be 0 for all the corners. It's not going to have any value because we are assuming that this chessboard is lying parallel to the plane, and that's why it does not have a z coordinate. It does not have any altitude. Uh, Now, what are the corners? So basically, we have to consider the dots or the corners which connect the black and white box in the chessboard. And if you'll go from left to right, you will find that there are 1, 2, 3, 4, 5, 6, and 7 different uh, corners. Similarly, we have 5 corners available if we go from top to bottom, and the total number of corners are going to be 7 into 5. That's going to be 35. Uh, the coordinate which is on the bottom right shows 7 comma 5 comma 0, but that coordinate is incorrect since we are basing our indexing on 0. It's going to be basically 6 comma 4 comma 0 because we'll be subtracting -1 because we are not starting from 1 and we are starting from 0. Now, what happens is the very first thing you need to do in the pipeline is you need to initialize the object points. So again, the points which we saw in the right side of the real world representation of the chessboard, we have to initialize our object points based on that. So you need points which would look like, which would start from 0, 0, 0 and till 640. You would proceed in the horizontal manner from left to right, and then you will come from top to down. So for example, the second corner would look like 0, 1, 0, and when coming from top to bottom, so 0, 1, 0, 0, 2, 0, 0, 3, 0. Similarly, going from left to right, it will be like 0, 0, 0, then 1, 0, 0, 2, 0, 0, 3, 0, 0, like that. So based on this, you initialize your object points, and then after that, you take few chessboard images in your pipeline. For that, the Udacity repository has provided some images, but if you want, you can also print a chessboard image on a paper and take some, click some pictures of that image in your uh, through your camera, and then you can process those images. So what you have to do is for each image, while processing in the loop, you need to grayscale it. Uh, you need to remove its color information, and then there is a OpenCV function called find chessboard corners. You need to call that function. That function is going to return you all the corners which are identified by it, and you can append those corner values into the image point array. So we have two arrays. One is the object points array and another is the image points array. So object point array consists of the values generated through the image shown on the right side, while the image point array would have values which we will retrieve using the find chessboard corners method. After appending the values to the image points, we can also draw the chessboard corners just for our visualization purposes. And then once we have this image points and the object points, we need to calibrate. We need to call the calibrate camera function of OpenCV, passing the original image and the image point and the object point. Um, and once we call this calibrate camera metrics, we are going to receive uh, in the result, we are going to receive a camera matrix, we are going to receive a distortion matrix, and we are going to uh, also get the rotational and translational vectors, but those are not of much use for us in order to undistort the image. So for now, we are just going to focus on the camera matrix and the distortion matrix. So the information which we get using the calibrate camera function, we use that information in the CV to undistort method, where again we pass the original image, we pass the camera matrix we just received, and we pass the distortion matrix. And based on that, we get a destination image and the final image, which is the undistorted version of the original image. And that's how you calibrate a camera, and you make the necessary correction for the distortion happen in the images captured by your camera. So this was the first part or the first topic of our webinar. That's all about it. If you guys have any questions for now, please let me know. Okay, so I guess we do not have any questions at this moment. So I'll proceed further with color spaces. So uh, color space is a specific organization of colors, and it provides a way to represent colors in the digital images. You would be already familiar with the RGB color space, which consists of red, green, and blue. So if all the values, the red value, blue value, and green value, all these three channel values are 255 or the maximum, it represents a white color. If all the values are zero, it represents a black color. Let's say the middle value, which is for green, is 255, while all other two are zero, then it represents a green color. And similarly, whatever the combination of these three values is, based on that, you get color which is generated from this three primary colors, which are red, green, and blue. So this is one color space. And now let's talk about what are the disadvantages of this color space. So you have one image taken by the camera of the road, and it has a yellow color lane line. And even though that lane line is available in the red and green color, it's not visible in the blue color, because yellow color is, it consists of red and green component, but it does not consist of the blue component, right? And in this various channel images, be it red color, green color, or blue color, whatever pixels you see as bright, those pixels have, for example, in the red channel image, whatever pixels have brighter colors, they would have more component of red compared to green and blue. Similarly, in blue channel, as you can see, the sky portion looks more bright compared to other regions because sky is blue and it has more component of blue present in it. So that's how this color channels work, and this is representation for the color information in an image. One more drawback of RGB colors is that, or the RGB color space is that under different lighting conditions, maybe if the scene is dark or maybe the scene is bright, based on that, certain colors may be detected, certain colors may not be detected. So it gets affected based on the luminous intensity of the scene. Uh, to remedy this, we have other color spaces which operate in a different manner. So two of those color spaces are like HSV and HLS. HSV stands for hue, saturation, and value, while HLS stands for hue, light, and saturation. So light, saturation, and value are going to have regular values, but H has these cylindrical values. As you can see, the representation is such that that uh, U is along the circumference of this cylinder. So we have 360-degree in a cylinder, and we divide it by 2, we get 180. So when we start from 0 till 179, that's the value which would be the range for our hue. And for saturation, lightness, and value, we do not have to think in the cylindrical degree terms. Now, in HLS color space, what happens is if we just focus on hue and the saturation channel and we ignore the light channel, then and we want to do some kind of color detection, then that color detection will be more visible, will be more doable, because in the HLS color space, the light related channel is a completely separate channel, and we can simply choose to ignore its value, or we may use it for some other purpose, but we may not use it for the light uh, uh, or sorry, the color detection purposes. So in our first image where we wanted to detect a yellow color lane line, if we'll use just the H and S channel, then it doesn't matter if there is a shadow or if there is excessive brightness, we will still be getting good values in particular ranges of H and S, which would let us know that okay, yellow color is present in this particular pixels of the image, and we may not have to rely on the lightness. And that's the advantage of using this color spaces. So the same image now is been separated in H, L, and S channel, and as you can see in the S channel, the saturation channel yellow color is being identified using with the bright pixels, with the white pixels, while in the H channel, the same has been highlighted using the black pixels. And in the L channel, it's very dull, almost as near to grayscale, so it's not possible to identify it. And you will see the variation when there is a shadow and when there is no shadow in the L channel, but you would not see such variations in H and S channel. So that's the reason this color spaces are more truthful while doing the color thresholding. So let's talk about this parameters H, L, and S and what they represent. So hue represent the color independently of brightness variation. So on the right side, you see various shades of blue color. Since all of them are blue, they all are going to have the same value of hue uh, and the consistent value of hue, because that particular value of hue is going to represent blue color and nothing else. So that's what hue is about. For each blue colored box, you may find different values of lightness, you may find different values of saturation, but for all of them, the value of hue is going to remain the same. Uh, Now for the lightness value, or the value in the HSV channel color space, HSV color space, it represents how light or dark a particular color is. So for this image, which you see about the red color, on the left side, the lightness is very low. As you move from left to right, the lightness increases, and that's clearly visible in the image itself, that most right hand side red color is the brightest one, while the left one is very dull, it's very dark. And for all of this, the U value is going to again remain same, because they all consist of the red color. The third uh, parameter is the saturation for HLS, and it basically represents the colorfulness of the color. So if some color is more closer to the primary colors R, G, and B, then those colors would have high saturation. If colors are more closer to the white color, they would have low saturation. Low saturation colors are going to look lighter, while the high saturation colors are going to look more intense, they are going to look more bright. So once we understand how this H, L, S, and V are working based on our requirements, we can uh, you know, apply some color thresholding on this particular channels, and we can extract, or we can identify particular shades of color we are looking for in an image while doing image processing and while doing computer vision operations. Uh, Over here in the slide, I have RGB to HLS converter. So there is one really nice website by Rapid Tables. I have provided the URL for the same as well. What you can do is, for example, you want to uh, find out the values of H, L, and S for yellow color. So for the ranges of yellow color, what you do is you first find out what are the RGB values for a yellow color. You put those and you convert those, and you get the HL and S values. Then you could use those values for applying the color thresholding in your image processing. The formulas are provided on the left. You can do the calculations manually, or you have the calculator directly available, so you can simply convert the values and leverage them in your project to identify what should be your color thresholds. So that concludes our session. If you guys have any questions, please let me know. So I believe there are no questions at the moment, and I'm going to conclude this session over here. But the recording for this will be available on YouTube. And if you have any further questions, if you have any doubts, please feel free to reach me out, and we can take those questions and discussions over our Slack channel. Thanks everyone for joining. Have a wonderful evening ahead. Thanks so much.